Okay, hello everyone. I just gave back the problem sheet number 1. I think it was generally well done. Maybe I can come back on 1 or 2 questions that were a little bit more missed. I'll be quick, but please, if you want to discuss them more, I'm available tomorrow. We can meet at some point if you'd like to understand what you don't understand, or if you'd like to know more. I guess the whole purpose of it, it's not to put a grade, it's really to get you to, well, an occasion to work some problems, so that it's not like I tell you something about how Turing machines work and then we forget because we haven't put our hands into it. I think it's good to put our hands into it. But also, if you get a chance to learn from what you don't understand, then please, I'll try to render myself as much accessible as I can, to make myself as accessible as I can. So I guess question 2 was there was a glitch. For some people, what was it again? It was how many prefix codes are there? By how many, I mean either countably or uncountably. And I originally wrote the question very liberally like that, but then I thought maybe it needs more specifications, and so I asked for prefix codes of the form like that, of a countable alphabet, because this is where problems can happen when we have a countable alphabet. By problems, I mean we get uncountably many prefix codes. So that is the answer. And I gave a hint, and it was to consider subsets of the form, actually subsets of that set. So why? Because only by considering a very restricted class of all prefix codes, we can still have uncountably many prefix codes. We can still see that there's uncountably many. Why? Well, technically this is not a prefix code, right? This set here, hi Jacobo. It's a set of code words. But we have a natural prefix code, which would be to map 1 to this code word, map 2 to that code word, 3 to that code word, 4 to that code word, and so on. And from this set of prefix codes, if I consider subsets of it, I would also have another natural code. So there's 2 kinds of subsets that I can take. I can take finite subsets, in which case I will have not enough code words. But finite subsets don't get me to uncountability. Infinite subsets do. So there's infinitely many, uncountably many infinite subsets of, let me call this set S. Okay, we can see that there are uncountably many because to specify a generic subset of S, I could see that as a yes or no, I take the element. Yes, I want 0 in my subset. No, I don't want 0, 1. No, I don't want 1, 1, 0. Yes, I want 1, 1, 0, 0, and so on. And this defines, if I put a 0, comma here, defines a real number, an infinite sequence of real numbers. So there's at least as many infinite subsets of S as there are irrational numbers, because it's a never-ending real number. And so we can see there's uncountably many infinite subsets of S. And then there's a prefix code in which I will map 1 to the first element of my subset that I just generated. I map 2 to the second element of the subset. I map 3 to the third element, and so on. I map n to the nth element. They naturally have an order. I keep the order, and there you go. I can have a prefix code for as many subsets. I can have a prefix code for any subset of this set, so at least uncountably many. There was another solution, in fact, was cleaner than using my hint. It was to realize that, yes, so what I want to do is encode n into ultimately s, but I could do a detour like this by encoding first an arbitrary permutation of n, and then using the, this canonical encoding in which I encode n to that I encode 1 to that code word, 2 to that code word, 3 to that code word, and 4 to that code word. So I fix a code here, like a canonical code that I could make with this set of code words, but I append it by an arbitrary permutation. Why not? And how many permutations are there from n to n? Uncountably many. So you can get into various arguments to argue that the number of prefix code is uncountable. I guess the other question that was a bit harder was the number 4. I asked if there was a prefix code of x. In fact, the prefix code of 0, 1 except the empty word onto 0, 1 star. With length equal to length of x plus log of length of x, take the ceiling, plus 1. Now there's no question, but the question is, does there exist such a prefix code? And we saw that Kraft's theorem was a criterion. Some sum converges. No, not converges. Sorry. Some sum is smaller than 1 if and only if there is a prefix code with the length as code words. So yeah, it boils down to wondering if 2 to the minus sum over all x in 0, 1 star. So yeah, I'm making more precise statement now, leveraging Kraft's theorem. This thing is smaller or equal to 1 if and only if there exists a code word, with these code word lengths. So if and only if the question number 4's answer is yes, basically. Okay, so we had to verify what was that sum. And well, that sum can be broken into 2 parts. It's a trick to see that. And so I have an index n, which will label the length of the strings. And because I excluded the empty word, my sum on n ranges from 1 to infinity. And then I have a sum for all x such that the length of x is equal to n. So those 2 sums together, at the end of the day, they sum over all strings. I sum over all n, all the strings of length n. So it does sum over all strings. And then we have 2 to the minus, well, length of x, now it's fun, it's fixed to be n, so 2 to the minus n, plus log of n, take the ceiling, plus 1. That sum is independent of x. So I sum over all n, I sum over all x, something that does not depend on x. So this sum creates a number, the number of times that I sum here. And that number of time is 2 to the n, because there are 2 to the n strings of length n. So let me just do that. I sum over all n. I have 2 to the n coming from that empty sum, which cancels out the 2 to the minus n here. Remains 2 to the minus ceiling of log n plus 1.
Minus 1.
Thank you. Thank you. Minus 1. That is what I'll just factor out 1/2 sum over n equals 1 to infinity. This is 1 over 2 ceiling of log n. And now that can get confusing, but what do I want? It should be quite clear that, yeah, let's do it properly. If I take the ceiling of log n and I compare it with log n plus 1, this one is larger, right? Log n plus 1 is going to be larger than the ceiling of log n. And so if I do 1 over 2 ceiling of log n, this will be smaller, no, greater or equal than 1 over 2 log n plus 1. Because well, taking 2 to the something doesn't change the order, but taking 1 over changes the order. All that to say that I can have 1 over 2, I'll have another 1 over 2 coming from this plus 1 here, and then I have sum n equals 1 to infinity of 1 over 2 to the log n. That is nice. 2 to the log n is precisely n. And that is infinity. So this sum diverges because that's the harmonic series. The harmonic series diverges. And so in particular, I cannot hope that it's smaller than 1. So if it's not smaller than 1, there's no prefix code of those lengths. Okay, and I won't do any more of it, but if you would like to discuss, I don't know, any other question, please come and see me. Questions on those problems? Good. Great, so let's retake the course where we were. In fact, last course we took a fun detour into Church-Turing's thesis. So the course before we defined the universal Turing machine, and we saw that it was not just a universal Turing machine, it happened to be a universal computing device to simulate many other models of computation, or many other ways in which we can understand computation. Now I want to get back into where we were. So with Turing machines and partial computable functions, we will keep on developing this theory today. Just as a small reminder, a function f from the natural to the natural is computable if a Turing machine computes it. This was our criterion. So we defined the precise meaning of what it means for a Turing machine to compute some function n to n. It involved, for example, encoding a bit string into natural numbers. It involved also defining correctly a single, well-defined output of a Turing machine, which we did with the head residing at some place after the computation. And then we can say, oh, well, the function is computed by a Turing machine if, that is basically encoding the input of the Turing machine, and that is going to be encoding the output of the Turing machine. Now, we also saw that we have an effective enumeration of Turing machines. And I'll phrase it as something new. The effective enumeration of Turing machines T1, T2, T3, ... provides an effective enumeration of all partial computable function. Which I denote phi 1, phi 2, phi 3, and so on. So the T1, T2, T3 is a Turing machine. You know, it has a head, it has a set of states, and so on. But we can understand them as computing some function. Which ones? Well, T1 computes phi 1, T2 computes phi 2, T3 computes phi 3, and so on. By abuse of notation, I said that I might sometimes change and write T1, write T2 as the functions. But if I want to be clear and I really want to be speaking of a function, I will be saving the symbol phi something. So phi is really a mathematical function, which is going to be a partial computable function. Computable is clear from this because we can understand it as being computed by a Turing machine. Partial, just as a reminder, it means that, you know, I wrote as a starting set natural numbers. But sometimes some function, let's say phi 3, might not be defined on some input. Maybe phi 3 on input 5 does not have an output. It's undefined. Why? Because maybe Turing machine 3 on an input which encodes number 5 may never halt. So that's why we say that it's a partial function, because it does not need to converge or to be defined on all inputs. Actually, speaking of which, we shall denote phi I of j, arrow like this, and ti of j, arrow like this, if phi I of j is defined, i.e. the Turing machine Ti halts on input j. And similarly, we're going to be writing phi I of j, arrow this way. Exactly. And Ti of j, arrow this way, if phi I of j is undefined, i.e. the Turing machine Ti does not halt. On input j.
So phi I of j would be equal to our funny undefined symbol.
Correct, yeah, it's a Oops. Thank you. I also used that at some point. But in what follows, I'll use this notation. I guess it just has a shorthand because I can have one system of notation for both. Oh no, this goes here. It was undefined when phi I of j was undefined. Yeah, this was here. Yeah, the advantage of this notation is that I can encompass via one system both concepts. It halts or it does not halt. Or I could just write is defined and is undefined, but there you go, that's what it means.
So you could maybe also extend the notation if you don't put the j, but we put a down symbol, like phi I down symbol would just mean it halts on all inputs.
Why not? Correct. While you're speaking about it, just realize that it's a function. Whether a Turing machine halt or not is a matter not just of the Turing machine Ti, but also on its input. I don't know, Turing machine number 16 may halt on some input and not halt on some other's input. That's like a generic behavior of some Turing machine. As Will mentioned, some Turing machines will halt on all inputs. By the way, these have a name. Can you recall the name?
Total computable?
Yeah, exactly. They're total computable functions, or functions that these Turing machines compute when they halt all the time. Yeah. Correctly. Okay, so that is just notation. And I feel I'm still like in the recall of what we're doing or introducing basic notations. But I only quickly defined the computable number. Now, let us be a bit more, take my time to define it a bit more properly. Let alpha in R, just in the spirit of Turing's paper, we saw that the title of Turing's paper was on computable numbers. And let alpha n, like this, denote the first n bits of alpha in binary expansion. Definition, a number alpha in R is computable if the function n maps to alpha n is computable. I remember I only briefly mentioned that, but we had not really written it down. To expand this definition, because I invoked the notion of a computable function, if I expand this definition, it means there's an algorithm which takes as input n and produces the first n bits of alpha, and then halts.
Yeah, I forget if you mentioned this, but I think you might have mentioned pi being computable because you can do like the alternating sum to get more and more digits.
Exactly. Pi is computable. Because there's many ways to generate the bits of pi algorithmically via an algorithm. And you can do it, and the algorithm knows how big is the error, so that you know that you have or not properly stabilized the first n bits of pi in your proxy for pi, and then you can compute those first n bits given n.
Do you know about like common numbers in mathematics that are not computable?
Yeah, we're gonna meet one. Yeah, 2 at least. Yeah. Yeah, Turing, I guess, exhibited the first uncomputable number. The reason why I remind you the notion of a computable number is that you're going to realize that once you have computable functions, well, we can extend this notion, and like the computable number is basically embedding the notion of computable function in a definition. And now we're going to go into define a computable set and a computable something else. And it's always going to be like, oh yeah, we have a notion of computable functions, and then we can leverage this definition to define whatever we want. So here we are. Oops. A set, capital A, as a subset of the natural numbers, is computable or decidable or recursive if its characteristic function is computable. And by characteristic function, I mean, I would actually call it D sub A. Okay, so a characteristic function of a set is always defined the same way. It's worth either 0 or 1. And it's worth 1 if n is in the set A, and 0 if n is not in the set A. Yeah, so please realize that this function d sub A is actually a function. It takes a number n, defined on the natural numbers, and it returns a natural number. In this case, it's going to be either 0 or 1. And it tells you if yes or no, n is an A. 1 is understood as yes, and 0 is understood as no, it's not in the set. So if I expand this, does there exist a Turing machine which expects an input n, and on all input, it halts, either with 0 or 1 as an output. And it's 0 or 1 is a precise signal of yes or no, this n was an element of A.
Well, I can see why you like decidable, because this is basically what defines decision functions.
Correct,
Complexity
yeah.
theory, P and NP and all that stuff.
Yeah, this Turing machine is a decider. It tells you yes or no. It decides if n is an A or not.
So is this your way of finding an element without enumerating everything?
Correct. You can invoke the decider to say, I don't mind about the other ones. I just want to know if 142 is in my set. So I'm going to input 142 in that algorithm. Eventually, it's going to halt. It's going to tell me 0 or 1.
Okay. So like in the previous episode, we had a situation where we would enumerate all Turing machines, and like we would stumble upon like a bad Turing machine and like stop there. So now we want to avoid that by trying the decider thing. Can we like decide directly where can we go? Is that the story?
Follow this episode. I like that you called the previous episode. I'm like giving a Netflix series here. Keep binging.
So part of it is like you can select what goes next.
Okay, so the Turing machine that computes dA is a decider. Of the set A. It decides if yes or no a given element is an A. Okay, so you already connect the notion of it's a decidable set because there exists a decider. Or it's a computable set because the characteristic function is computable. These two things are two ways to think about it. I used to do my examples in blue, but now only the blue marker works today. So the examples are still going to be in blue. Example. It helps to have some examples. All finite sets are decidable. Why?
I can see the successor. I can compute the successor of each element, so I can compute all the set.
You can just do a linear search and you get if the element is inside the set or not.
What do you mean the successor? Like
I start from 0, I add 1, and if I is that number, it is in the set. And if I cannot reach, if the Turing machine else is not. But of course, the Turing machine will never halt because I always can count to reach a natural number.
But you're invoking the successor, which makes me think of an infinite set. I say all finite sets. You have a finite set, and I want an argument to tell me why some generic finite set is decidable. Pasquale?
Because you can just do like some linear search on the set.
Yeah.
And if you meet it, it's fine.
Yeah.
You're done. Otherwise, if you end in this, if the set elements of the set finish, like you just return false. I mean, you return 0.
Yeah. You have to think of a Turing machine. The Turing machine might be a messy one. It might have like a huge table embedded into it, or an algorithm. Now that we have seen the church Turing thesis, please think of your favorite ways of programming algorithms. So you have to think of an algorithm which, on a given input n, it's going to halt and it's going to say yes or no. It's in the list. It's in the set. But if the set is finite, you can sort of hard code all the set in the name of a list, a table, in the algorithm. And then as Pasquale said, you reach n and you look in your list. Is n in my list? No. You output no. Is n in my list? Yes. You output yes. It's a finite algorithm. It's going to halt all the time. I'm just going to write list. Finite list. You see that for infinite sets, that strategy won't work. Because if there's an infinite set A that I want to use this strategy, then it's not going to fit in a finite Turing machine, that list of elements. But fortunately, there are many other infinite sets that are still decidable, because we can do more clever things than just hard code the list of all elements. So this was one. Now I'm going to name 3 other ones, I think. Yeah, the set of odd numbers. The set of primes. The powers of 17. Are all decidable sets. I give you a number, you have to tell me yes or no, is that number odd? There's an algorithm which decides. You only look at the last digit, in fact. If it's 0, 2, 4, 5, 4, 6, 8, you say yes. No, you say no, it's even. Otherwise, you say yes, it's odd. There's a very simple algorithm. And that is regardless of the number you receive. There's also an algorithm which on input n says yes or no, this number n is a prime. And similarly here, it receives a number, it's going to do its thing, and it's always going to halt with some answer, yes or no, it is a power of 17.
Like just checking all the multiples of 17 or something.
That's one way. Or get your number n, try to divide it by 17 with your familiar high school method. Maybe that was elementary, I can't remember. And if you have a rest, you say no, 17 doesn't divide n. Oh no, sorry, that doesn't work. Powers.
Yeah.
You just
Yeah, it's
Oh yeah, it will work, but I have to iterate the idea.
until you reach one.
Notice that we're very far from actually programming a Turing machine, but I don't mind. Now you're gonna have to think of a generic algorithm that does the job. Yes or no. It halts and it says yes or no, it is or not a power of 17. Questions? Let's keep going a little longer. I think, Vol, I'm heading to what you have in mind. Let A be a subset of the natural number. And enumerator EA of the set A is a Turing machine that enumerates all and only, I'll put that in parentheses, elements of A. Without order, and possibly with repetitions.
Why without order? We're just making it less relaxed, or like a more relaxed condition, or it seems like the ordering would be natural for an enumerator. It's just spitting them all out.
It would be too strict a condition to demand that when it's spitted out, it needs to be in order. By the way, when I say order, I mean the order of the natural numbers. Like that's implicit. We have a set which has a natural order. That's what. And then when I say without order, it might be the case that my enumeration outputs 100 before it has outputted 81. So I'm losing the order.
So any Turing machine is full up to permutation.
It's what you say.
It's cool to have any Turing machine up to permutation.
It's not. That's not exactly the idea. We'll work out the power of this notion soon. So far, what have I said? So an enumerator of a set A is a Turing machine that enumerates all and only elements of A without order and possibly with repetitions. I should add that generically this computation does not halt.
Yeah, I mean, unless it's a finite set.
Correct, because generically we could have that A is infinite, in which case forget it, it cannot halt. I have to enumerate all elements of A, so I'll start with the first one, not in order. I'll start with one element of A, and then the Turing machine will output another element of A, and another one, and if it's infinite, then it can never stop. But what does it mean to have output them all? It means that eventually, regardless of which element is in A, eventually it will be enumerated. But it can also not halt for a different reason. It can also be the case that A is finite, like this. But the enumerator, well, EA, keeps on looking for elements of A. Forever, even if it's done. In other words, it might not know that it's done looking for elements of A. It might just be keep on computing, because, for example, it might not have in advance how many elements there is in A as a promise. So the enumerator might even not know if there's infinitely many or finitely many elements of A. It just produces some numbers. All the numbers that it produces are in fact in A, so it's never like giving us something that is not in A. It might output twice the same number. That's fine. Repetitions are allowed. And there's no orders in which he outputs them.
Speaking of repetitions, what about if you have, for example, just two elements that it's supposed to spit out, but for whatever reason it keeps spitting out the first one, like forever?
Well, then it would not be an enumerator.
Because it has to eventually spit out the second one.
Correctly.
We don't know how far in the future, but at some point it has to.
Yeah, it has to enumerate all.
Yeah.
Eventually it has to be enumerated.
Okay.
Questions? Have a good break. See you at past. Okay, we're gonna start again.
Then I go to like Rod.
We saw that computable sets or decidable sets sort of involve a special kind of Turing machines, which we have called a decider. It's a Turing machine that expects an input n and says yes or no. That n is an element of A, the set that I'm deciding. Now, inspired by the concept of a decider, we invent or we write down a new concept, an enumerator. Why not? We could, instead of viewing the notion of connecting computability to a set through deciders, we might want to connect computability of a set through enumerators. An enumerator of a set is gonna, it's gonna output some A17, A132, A2, A17, where I am writing the suffix as I involve some order in my set A, because my set A is fixed, and it really does have A1, A2, A3, and so on. And suppose it's more interesting when A is infinite. But my enumerator is not required to output A1, A2, A3, What it is required to output is a bunch of A's. Whenever it outputs A something, it really is an element of A. It's not bluffing. But I don't mind about the order. So in this case, it's outputting A17 and then A132. the 132nd element of A, and then for some reason the second, and then A17 again, like, yeah, I knew that one, please give me something else, and it's gonna give me something else. It never halts, but at the end of the day, this set, if I put a pair of brackets around it, it's a set, and it's equal to A. You know, once you put if you have this set notation and you write A17 twice, in set notation you don't care. Like A17 collapsed to a single element, and all elements of A will be enumerated. That's one way to write it, or the other way to write it we have already done. So that's an enumerator. Now I'm ready to define something else. Definition. A set, a subset of the natural, is computably enumerable or recursively enumerable if it has an enumerator.
Push up the board just so I can see the definition real quick on the last one.
Sure.
Okay. Yeah, so an enumerator is a Turing machine. Okay.
Yeah, but it has an enumerator. I don't really like my formulation, but if there exists EA, right? It seems like it's owning somebody, but it's not really the case. Recursively enumerable is still used a lot. But since I saw that some authors are changing it to computably enumerable, I will do my best to use computably enumerable in the course. Examples. The following sets are computably enumerable. First, all decidable sets. Just recall you, the A of n was equal to 1 or 0. That's a reminder. So I'm claiming that all decidable sets are computably enumerable. Why?
Just start passing one string one by one and just see whether. If it's 1, you just print it out.
Yeah, great. The decider always halts. It's never a problem. So, yeah, I'm going to try first dA of 1. It tells me 0 or 1. If it says, and then I'm going to do dA of 2 and dA of 3 and so on. And if dA of 1 says 1, then I'm going to enumerate 1. If it says 0, I'm not going to enumerate 1. because it's not in the set A. And then dA of 2. Yes or no? Yes, I enumerate 2. dA of 3. Yes or no? No, I skip 3. dA of 4. Yes or no? Yes, I enumerate 4. Note, by the way, that in this case, I'm enumerating them in order, which fulfills the criterion of not taking care of the order. Not taking care of the order is a more liberal thing. If in this enumeration the order happens to be there, why not? I'm not going to prevent it. So yeah, it says yes or no, yes or no, yes or no, and suppose that this is what happens. Yes, no, yes. Then you enumerate 1, you don't enumerate 2, you enumerate 3, and so on. That's how you use the decider to build an enumerator. Okay, second example is it's a little random, but sometimes it's good to have random things. It's not random, it's just like, it's not profound in computability theory. The set of pairs n comma m. It's, by the way, it's numbers, right? It's a single number, but we know how to encode a pair of numbers in a single number, so it's the set of natural numbers that correspond to an encoding of a pair, such that, n is the largest number of consecutive zeros in the first 2 to the m digits of pi. N is the largest number of consecutive zeros in the first 2 to the m digits of pi. And now this definition, I'm sort of assuming that we write pi in decimal expansion. Why not? This is the way I define this set. I can see how I can write a program which is going to enumerate all these pairs. It obviously embeds a program for computing pi. I will need many decimals of pi, as many as I need. But at the beginning, I can start with what I have in my memory of what pi is. And yeah, when m is equal to 1, the first 2 digits of pi contains no zeros. So 0, 1, I can start enumerating it this way. 0, 1 will be enumerated. I will also enumerate 0, 2, because there's no zeros yet in the first 2 to the 2 digits of pi, namely in the first 4 digits of pi. I will enumerate 0, 3, because in the first 8 digits of pi, there's also 0 consecutive zeros. Eventually, I will reach 1, 0, so there will be I think it happens quite, not for the next one, but whatever. At some point, it will be 1 sequence of 0 in the first 2 to the 5, say, digits of pi. Eventually, there might be 4 strings of 0 in the first 2 to the 7 digits of pi. But we can compute this and enumerate all these pairs.
But this is also recursive, isn't it?
It's in, yeah, I think it is, yes. It is. You're right. Yeah. Special case of 1. Yeah. Actually, I think it is recursive. So by which would mean I give a pair nm, and you have to tell me yes or no. There is n is the largest number of consecutive zeros in the first to the m digits of pi, and you can say yes or no. So I try to come up with an example in which explicitly you use the enumeration structure, but as Lorenzo remarked, I'm basically again in the case number 1.
I think a nice example could be like the set of Gödel's numbers of Turing machines that halts with 0.
Yeah.
Example.
That's my third example.
Okay.
Yeah. Yeah. I really wanted you to get into some mindset of enumerating things from some structure. Yes, now it's going to get more interesting in, say, point number 3. The set of indices I such that the range of phi I is not empty, non-empty. So these indices, you know, I had my enumeration of Turing machine, which define enumeration of partial computable function. We call these the indices. Some partial computable functions will have an empty range. An empty range means that their image is nothing. In other words, the Turing machine that computes that halts on no input. It never produces an output. Well, what I want is a set of indices of those partial computable functions for which the range is not empty. So not those.
Sorry, how can halt without computing an output?
Ah, sorry. Yeah. Good question. Good point. If I did say that, I was wrong. Thanks. It never halts on no
Never
input.
halts, okay.
Yeah, it's the only way of not producing an output is not to halt. Because even if it just halts and has nothing, then it computes the empty string, so the number 1 in my construction. Thanks. Another way to write that set is this one here, for those who prefer this notation. I such that there exists a J for which phi I of J halts. Yeah. So I claim that this set is computably enumerable. For those who have never seen a course like this before, it's a tricky trick. And I would like to let you think about it a little bit. How can I enumerate all those i's such that there exists a j for which phi I of j halt? It might be tempting to say, damn it, let's start. Let's compute
Machine number 1, input number 1.
phi I of 1. Let's compute this. All right, it's my first one. But if it doesn't halt, you're stuck.
Yeah.
You're not enumerating anything. You're just stuck in a loop from step 1. So at some point you have to get bored of trying to compute that. You have to go to another one and say, you know what, I have done enough of this. I'm going to keep it for later. And I'm going to compute phi 1 of 2. A little bit. maybe it's not gonna halt, and I'm gonna get bored of phi 1 of 2, and I'm gonna compute phi 2 of 1 for a little bit. And at some point I'm gonna compute phi 1 of 3 for a little bit, and phi 2 of 2, and phi 3 of 3, and the little bit that I'm computing is going to increase gradually. And if I happen to get, and I'm going back to phi 1 of 2 and compute it for a bit longer, eventually if it halts, then I know, oh, 1, the machine number 1 has at least one input for which it has a valid computation. So its range, it's not empty. So I will enumerate the number 1. But now let me formalize this idea of computing a little bit for a little bit of time and increasing these bounds. That's actually an important construction. Once you see it, you use it often. So, in other words, we will be using these kinds of construction again. So in other words, it's worth understanding it and making it clear now. For each, or for k equals 1, 2, 3, and so on, k is going to be increasingly larger. Simulate all of those Turing machines. Ti on input j for I and j smaller or equal than k. And I'm not going to simulate them completely, otherwise I might get stuck in a hole, namely a non-halting computation. So I'm going to simulate them for k steps. I'm going to simulate them for k steps of computation. When some Ti of j halts, I'm going to say, oh, cool, the partial recursive function number I has a non-empty range. So I'm going to output I.
And you no longer need to simulate it in further steps.
You're right. If I happen to ignore what you said, I might re-output I. If I realize that, oh, the Turing machine I also halts on J prime,
Okay.
I will re-output I,
That's
but in
also
my
fine.
definition of what an enumerator is, I don't mind if I is repeated. That's it. It's a simple idea now. It's worth verifying it works. Okay, let me just, before verifying it works, let me tell you what we've done. Let's say k equals 3. I'm going to come back. I'm now at step number 3 of my iteration. I'm going to relabel those in a way that makes more sense than what I did. No. I'm at step number 3. I'm at k equals 3. So my algorithm says simulate all Ti of j for I and j smaller or equal to 3. This means simulate all those 9 computations. For how many steps of computation? Just three steps of computation. Normally, Turing machines don't halt after 3 steps of computation. So probably that after that step, I'll go like, oh, none of them has halted. And then I enlarge my matrix to 4 by 4. And I'm going to simulate all 16 computations for 4 steps. And then I enlarge that 5 by 5, all 25 computations for 5 steps. And remark that it works. If that one halts in, I don't mind, in that many steps, eventually K will be as large as that many steps. So eventually I will be recomputing the things I've always been doing, and I'll realize, haha, that's a halting computation. So I will output 2, because that's what I need to do. I need to output the i's such that there exists some j for which phi ij halts. My enumeration will find it out that machine number 2, or the partial computable function number 2, has a non-empty range. Boy. What do I write here? Yeah, let's check. Or notice that if phi I has a non-empty range, there is some j and some t such that ti on input j halts in t steps. Right? If it has an unempty range, that means it's defined on some input. That's the input j. If it's defined on some input, it means that on that input, the Turing machine ti is eventually going to halt. And the way I wrote it here, it just means there exists some time, t, for which it has halted in that number of steps. T might be very large, it might be much larger than j, which might be much, much larger than I don't mind. It's all finite numbers. Eventually, and I'm going to be more precise about what that eventually means, namely, when k is equal to the max of I, j, and t, because k is this parameter here which keeps on growing. And k rules 3 things, basically. It rules the index I, it rules the input j, and it rules the number of steps of computation. So eventually k will be the maximum of all of these. And in which case, the enumerator will find out we'll find it out. The it refers to the fact that Tij halts and T step. It will eventually find this out. And output I in the enumeration. Well, that's clear. Output I. So it does output all elements of A. Now let's make sure it doesn't output more elements than A. A here is my set, this set. If phi I diverges for all its input, well, the enumerator will never output I. It will keep on increasing its k. It will keep on checking phi I on larger inputs j for longer times k, t. But this machine phi I just always diverges. It always loops for any input. So the enumerator will not make up something, which would be something wrong. Questions about this recursively enumerable set or computably enumerable set?
Is this computable? This set.
Would be a nice homework question. Thank you, Will.
You're welcome.
I remember a different definition of recursive enumerability, which was instead of the characteristic function being computable, you had like the semi-characteristic function being computable.
Thank you. My God. Lorenzo, I'm happy you're here. We're having a dialogue. It's the next thing I'm going to say. But never repress those comments. I love it. You anticipate and it... beautiful. Yeah.
Does this trick work because, let's say in that case, the matrix has a countable number of elements?
Yeah.
Otherwise, it will not work.
Yeah. I wouldn't see how it could not simulate them all. Yeah. Definition. A set A, also subset of N, this becomes routine, is recognizable. Or semi-computable. if the following partial computable function exists. Which one? I'm going to call it RA for recognizable. RA of n is also defined. It's very similar to the decider. We could call it the recognizer if you want. And if n is in A, it's going to recognize it. It's going to say yes or 1. If n is not in A, might not be able to tell. It might be able to tell. So it might say 0, or it might just loop forever. So let's say this is no or silent. It keeps on computing forever. So I guess this is the meaning of semi-computable. It semi-computes this set in this following way. Recognizable, I think, is funny. It's like, oh, I can recognize when you're in A, but I cannot recognize when you're not in A. Proposition. A set A is recognizable, no, is computably enumerable. If and only if it is recognizable. Okay, so we built this notion of enumerators. A set can be enumerated by a Turing machine. Now there's also this notion of recognizers, or the notion of recognizability or semi-computability. These two notions are equivalent. Perfect. Proof. Let's start with this side, which means that it is computably enumerable. The set A has some EA, enumerator for the set A. And what I want to do is to build a partial computable function RA, which will recognize the elements of A. How can we do that? We can enumerate all elements of A, one by one in no order, sometimes with repetition. And I want to build an algorithm, yes, a partial computable function, which says yes when it's in A. And it might loop forever when it's not in A. How can I do that?
Compare it with the enumerator's output. Then say yes.
I let go the enumerators, the various outputs. Yeah. until, you know, like RA has n, is given n, and its job is to say yes or no. So I run the enumerator, and I wait until I see n coming up. If n comes up, it means it's been enumerated by EA. It means it's in A. So I can accept. I say I can return 1. If n is not in A, the enumerator will never produce it, will never output it. But that's fine. The machine will never halt. It's waiting for n to be produced, but n will never be produced. Yes. So on a given n, yeah, realize that we're mixing two concepts. EA has no inputs. It basically has embedded in its rules, it has the information about A, like what it's trying to enumerate. RA is a partial computable function which has an input n. So what I want to do is construct a partial computable function RA. So I'm starting with its input. On a given input n, run the enumerator EA until n is outputted. And then accept it. Accept n. Accept n is just jargon to say map n to 1. This is our accept. Let's just check that it works.
Wait, what if it doesn't output n?
Yeah.
You just go on forever.
Could make it run forever.
The enumeration will most likely never halt. It never halts.
Yeah.
And so will you. You being the RA function. You don't halt. But that's fine.
Oh,
You loop.
okay, right. RA being the up arrow doesn't mean that it halts and spits out something. It means that it just doesn't halt.
Yeah,
It's
correct.
Just running forever.
Yeah. RA of n being the up arrow means
Yeah.
you're looping forever. It's an undefined computation.
Okay.
So my little check was if n is in A, it will be enumerated and RA of n equals 1. It will eventually accept it. It will find it out. On the other hand, if n is not in A, n will never be enumerated. And the vain search will never halt. As required. We are always more comfortable with decidability. We like when the algorithm will output something all the time. Now, recognizability is sort of might be a bit frustrating. When n is not in when n is not in A, it never halts. But if suppose you're the user of that algorithm. You don't have the information that it's not an A. Because you have run the algorithm for the age of the universe and it has not yet halted. Does that mean it's not an A? Because it will never halt? Or does that mean that it's still computing and eventually it's going to halt and tell you, oh yeah, n is an A? There's this frustrating part in the notion of semi-computability or recognizability, which I'm proving is equivalent to the computable enumeration concept. Now we've done one direction, and let me just finish with the other direction. That means we have a partial computable function which recognizes A, and we want to take it, use it, to make an enumeration of all the elements of A. Any ideas?
The same trick as before.
Yeah.
We have to do the same trick as before. Again, the trap is to say, oh, I want to enumerate all elements of A. Let me just go, don't write it down. RA of 1, let's compute that. I'm going to check if, yes, 1 is in the set A. But what if 1 loops? You're stuck in a hole again. So you have to spend time computing this, but not too much. Eventually you have to get bored and move to some more interesting problem. So eventually, allocate some time here and then compute RA of 2, and then compute RA of 3 for a little bit, and then come back. As Giacomo said, same trick as before. So for K equals 1, 2, 3, run the following computations. R A of n for n smaller or equal to k. So you're going to compute RA of 1, RA of 2, RA of 3, until RA of k. How long? 4k steps. Of computation. Now, once you've found this trick, the natural thing to do is to say, oh well, if you find a halting computation which says 1, then you have found a good n, an n that is indeed in the set A. So output that n, which is what we're going to do. If some n is found, for which RA of n equals 1, it means n is an A, and so output n. Enumerate that n. And I won't write it down, but observe for yourself that if n is not an A, then either this computation will halt and say 0, in which case you've been signaled that it's not an A, so don't enumerate it, or it will never halt, but that's fine, you will never enumerate it. You will never output it in your enumeration of all elements of A. quickly. If n is not an A, n will not be enumerated. There's a few holes to fill up for yourself, but it should be good. Questions? I think it's a good place to stop. We'll meet us on Thursday, and we're gonna finally get to the halting problem.